We continue with how does feedback affect angular momentum build-up in galaxy halos.
All right, so first of all, thank you to the organizers. Interesting conference already that we've been talking about, and I expect much more interesting stuff to come. So today, I'm going to be trying to answer the question of how does feedback affect angular momentum buildup in galaxy halos. And I put a little star there next to feedback because it's not just different feedback schemes I'm going to be looking at. We're actually going to be looking at different simulation codes as well and trying to look at angular momentum buildup and these different codes with these different feedback. So of course, anytime you're comparing different simulations, it's a massive collaboration. And so note all my collaborators down here. So give a little motivation. Suppose I run a hydrodynamic cosmological simulation on, for example, so this is what we're going to be doing, a Milky Way-sized galaxy halo. And then I tell you from my simulation some property about the halo, how its stellar mass grew, something about the cold gas in the halo, something about the angular momentum. The question you may then have is, how robust is this information that I'm giving you? Does it depend sensitively on exactly how I tweak my star formation? How do I tweak my feedback? What if I ran this in SPH? What if I ran this in a grid code? What if I ran this in a moving mesh code? Is anything that I'm telling you actually robust, or does it depend on who's running what code? Now, obviously, this is a very tricky question to try to solve. We're not going to kind of answer that broad question today. And I'm going to outline kind of two kind of basic approaches you might consider in trying to answer this issue. One is try to get all the experts of all the codes to agree to try to implement the exact same physics across all the codes. And then if you run the exact same initial conditions, you can try to compare and see, hopefully you get similar types of galaxies because you're supposedly running the exact same physics. For example, the Agora project, trying to do this initially and move on from there. That's a little more ambitious than we're trying to do with this smaller collaboration. So instead, we're taking kind of a flip side of that coin. Let's just look at some of the typical hydrodynamic cosmological codes that are being used in the literature and kind of just take each of their typical feedback schemes that people often use, whether that's thermal feedback or kinetic feedback or this or that, and then run the exact same initial conditions. And here, if something is different, it's hard to say exactly what's going on. Is it a code thing? Is it a feedback thing? So what we're going to be looking for is there at least some things that are the same regardless of what code, what feedback you're using from kind of up-to-date, modern kind of feedback schemes. So that's kind of the broad picture of what we're going to be doing. I'll introduce our simulations in a second. The motivation for this, for our kind of approach here, is we're interested in angular momentum, in part because of kind of what I'm going to call a new picture, or at least new emphasis in recent works, looking at angular momentum acquisition in galaxy halos. Cited a few papers up there. I'm sure there's more as well. But the basic picture, when you have fresh accretion to galaxy halos, this freshly accreted material has more specific angular momentum than kind of the cumulative total of all of the past accretion history. In addition, if you look at kind of filamentary accretion versus non-filamentary, or maybe phrased another way, cold mode, cold flow, gas streams versus kind of hot mode accretion, we find that the cold mode gas, or the filamentary gas, has higher specific angular momentum as it comes into the halo than non-filamentary accretion. And one of the results of this high angular momentum material that we brought attention to in the past couple of years, or some of our papers, are these things that we called cold flow disks. Essentially what you have here, so these are very large kind of snapshots here, 200 co-moving kiloparsec widths in these panels, showing a couple of our simulated galaxies from our 2013 paper where we used SPH. What we found was that the filament accretion, the cold flow gases that came in, had such high angular momentum that it created these massive disks of accreting material. That they only stayed in the halo like this for a couple dynamical times. So you can think of them as kind of sinking down to the center as they spin around a few times as the gas is being accreted to the halo with this very high angular momentum. So one of the kind of the predictions that we made from this paper is that you should see things kind of like this. In general, we said accretion should be roughly co-rotating with what the galaxy is doing. And as well, sometimes it makes these cold flow disks. We ran 4 simulations in that case, and at some point along the history of each of those Milky Way-sized galaxies, Each of them had this cold flow disk structure at some point. Obviously, it's not universal at all times for every galaxy. They all had them at some point. But the question we had was, again, how robust is this prediction? Is this some weird little quirk of SPH? Did this depend on exactly what feedback scheme we were using? What would happen if we ran something like this in a different code with different feedback? Would we still get this? Or is this some little quirk of our particular setup? So that's the motivation behind what we're doing. The Scylla project, named after the mythical multi-headed beast, the beast here being cosmological simulations with all their various heads. So what we've done is we've run the same initial conditions. So it's a Milky Way size zoom-in cosmological simulation using the kind of recent physics. So the parentheses here are just kind of papers that have been published recently, and obviously not an exhaustive list, from which we have very similar feedback, physics, implementation. The only exception is any of these papers where they have black hole AGN physics, we've kind of taken that out. One thing at a time. Let's just look at all the other physics first before we start tackling the AGN black hole feedback beast. And so some of the simulations that we're talking about today, we have Aripo, Enzo, Ramses, and we have the new PSPH gizmo code with the fire feedback. We are also running ART simulation as well, the same thing. We won't be talking about today just because I haven't gotten around to the analysis yet. So some of this is preliminary work, but eventually we'll have that comparison as well. So the common initial condition that we are using is taken from the ENSO run, so Young et al. 2012. The minimum dark matter mass, 1.5 times 10 to the 5, spatial resolution less than 100 H-inverse parsecs. So pretty good resolution there. And one key for trying to compare these things apples to apples is that we use the exact same analysis routines thanks to YT. So YT is an awesome platform for analyzing different simulation types in the exact same way. Now, again, in progress, so not all of our different simulations have been run all the way to Z of 0. So we're going to talk today mostly just about from Redshift 3 to about Redshift 1. One other thing I should note, unfortunately, in the transition process, Ryan Young left academia, left the field, and in that transition, we just lost due to a technical error the Z of 2 snapshot of ENSO. So at some point, I will show Z of 2. You'll notice that ENSO suddenly disappears. It's just because, unfortunately, we don't have it. There's nothing we can do at this point. So, there it is.
Are cooling recipes the same? It's always added cooling for all of them?
If I started getting into all the different, they're all completely different. Each of these kind of takes the kind of popular implementation from recent paper. So the coolings are different, the feedbacks are different. Some of them are thermal, some of them are kinetic, some is a combination of the two. If I got into all those details, like my whole talk would just be the details of the different codes. Okay, so first up, let's look at Redshift 3, and we're just going to look at the top 4 panels are showing just kind of gas density projections through a cube that has a width of 4 virial radius. That is, we're looking at material roughly within 2 virial radii of the halos. And you can see kind of roughly the same thing is happening. So good check so far. We have a filament kind of going from our bottom left to our top right. In all the cases, the filament's feeding onto the galaxy in all cases. You have various stages of diskiness being formed. So obviously the precise morphology is probably not something, at least in gas, that we could say is robust because it does not look exactly the same. In particular, you can even notice that the precise locations of these little miniature galaxies that are in the process of merging, not all in exactly the same place, so the timing is slightly different. In fact, I believe the Gizmo one just experienced a merger, I think, at this redshift, which is why it's a little kind of crazy and clumpy there. But even more different, if you look at the temperature maps, so kind of density-weighted projections of the temperature maps, very different again. So how much does this pollute the CGM or the IGM? Like how do the metals spread out? What's the temperature around this thing? How does the temperature interact with the cold flows that are coming in? Are going to be very different. But again, we're not trying to look at the differences. We're trying to see is anything the same. Is anything the same even though we have very different galaxies? Is anything the same? Well, hopefully something's the same.
They are printed out with the same color table.
They are printed out with the same color table. They are. So that is the same. There are a few things that are the same. I didn't have time to kind of include them in my talk in terms of the actual plots. But thankfully, the mass within the virial radius, the total mass, that tracks each other very well. That doesn't matter which code you're using. Thank goodness, if that was different, we'd really have a problem. Also, the total gas mass within the virial radius turns out to be very similar in all the different runs as well. Now, what fraction of that gas happens to be cold versus hot at a certain instant, that depends on which precise feedback code you're using. So if you're talking about cold gas halos, hot gas halos, it depends on who ran it. But if you're talking about the total gas mass or total virial mass, then it's about the same. Similarly, the star formation, as you might imagine from these different pictures, the star formation rates versus time, wildly different. So what actual galaxy do you end up with? What stellar mass? That's, again, going to depend on who ran your simulation.
So what's the resolution? You say 95-PASC. What does that mean for different codes?
The most refined spatial element is 95 parsec. Yes, I believe so. Okay, so now what we were trying to focus on, obviously there's lots of things that are different. Let's try to see if something's the same. In particular, we were interested in this angular momentum question. So one of the things we noticed in our paper a few years back was if you looked at the spin parameter of just the gas versus dark matter, we know spin parameters of dark matter halos should be roughly 0.04, kind of on a mass invariant scale. But what we noticed a few years back was that the spin parameter of the gas was significantly higher than the dark matter. So is that something that was robust, or was that a weird SPH thing? So we've plotted the spin parameter versus time from redshift 4-ish to 1 in our galaxies here. So we got our 4 different simulations. Now, if you're asking the question what is the spin parameter of my galaxy, then you're not going to get the same answer. But I would like to see, is there anything that is the same? I would like to see some kind of qualitative trends here. In all of our simulations, we have the spin parameter of the gas being more than the dark matter. The gas has higher specific angular momentum than the dark matter, almost no matter how you ran your galaxy. And with the exception of one weird time snap for Ramses at redshift 1, at every other moment in time for all different galaxies, the cold gas in particular is spun up more than the hot gas. So the cold gas in the halo has a higher spin than the hot gas as well. Now this is consistent with the picture I was telling you earlier with the angular momentum being built up by the cold flow accretion. The cold gas having this high angular momentum, that resulting in cold flow disks, etc. So that can ask the question then, if I still have this case that the gas has higher spin than the dark matter, do I still get these cold flow disk things? Well, let's start really zoomed out before we get to the halo. So we're looking at material within 4 virial radii here. And we first just wanted to ask the question of kind of what does this look like if you start doing line of sight velocity maps of what this gas is doing. And I know there's colors all over the place. This isn't just an art piece, but it's actually trying to be science. So if you look at this top filament that's flowing down into the galaxy, you can imagine if you have a 3-dimensional filamentary structure feeding onto a galaxy, you impose kind of an arbitrary line of sight, odds are your line of sight isn't exactly perpendicular to the filaments. They're flowing kind of towards you or away from you, depending on kind of the orientation. And what we notice is that this top filament that's feeding the galaxy is clearly, it's all blue shifted, line of sight velocity. And so that filament's kind of flowing towards us and down as it feeds the galaxy. Whereas these bottom 2 that are flowing up towards the galaxy, they're both projected in such a way that they're both redshifted, moving towards the galaxy. So hopefully not unsurprising, right? You have these things flowing down, feeding the galaxy, and so some of them look like they're coming towards us, some looks like they're going away, redshifted and blue shifted. But one off to the side actually is kind of perpendicular to the line of sight, so it's much more variant from code to code. But all the codes agree that the basic flowing structure of the filaments are about the same. If we zoom into the virial radius now, what we see is that, depending on your code, different feedbacks are doing different things to the disk. And so what's the extent of the disk? What's the kind of morphology of the disk? That's going to depend on your code. But because we have this top filament in all cases feeding from the top, blue shifted, we get this same kinematic signature within the virial radius as well, in the halo of the galaxy. And because you have these bottom 2 that are feeding it and they're redshifted because of the orientation of the filament, you still get this redshifted element feeding onto the galaxy within the virial radius. And so you can imagine if you have these cold flows that are flowing in along the filaments, There's some non-zero impact parameter. As they get near the halo, they're naturally going to start spinning around the center, and you get these, maybe they're not all of these are nice, pretty disks, but they're certainly cold flow rotational things, wherever they are. Now, it wasn't just this special, I didn't just pick some special moment at redshift 3. What if we jump down to redshift 2? And again, we unfortunately lost Enzo, but we have the other 3. Here's the very large scale structure, again, within 4 virial radii. You can see the movement, the flowing of the filaments with this line of sight projection. You have blue shift on the bottom, red shift on the top, and we look within the virial radius, and again, we have this kind of coherent flowing where you can kind of just cut the galaxy in half, and you have this nice rotation being funneled and fed by the cold flow gas coming in along the filaments. Now again, exact detailed structure. Gizmo's a little messier than the other ones, but even there, if you kind of draw an imaginary line, you can still see kind of red shifted to the upper left, blue shifted to the bottom right as it rotates around the galaxy. And they're starting to look more like disks now. The accretion process isn't quite so quick and messy. Even as you go on to redshift 1, now here we only have 3 just because our repo simulation is still running and it just hasn't hit redshift 1 yet. So again, preliminary, eventually we'll have more comparisons. But again, larger scale structure. Now the filaments aren't as dense anymore, so I had this kind of arbitrary density threshold to plot them on this map, so you don't see the filaments quite as easily, but you can see that signature of the filamentary accretion on very large scales, again, by the fact that the tops are all redshifted and the bottoms are all blue shifted, but because you don't have a perfect perpendicular alignment of the filaments. And as you zoom in again, you see the red-blue nice rotation signature as well. Now note, this width here is the virial radius of the halo. So it may look in these panels like these are small little disks. Like what do you expect? You're making a disk galaxy. Of course it's rotating. But this is like 100 kiloparsecs across. So this is not the scale of just the galaxy. These are, in essence, what we called earlier cold flow disks. This cold flow material making these massive extended disks.
In the gizmo,
Yeah.
you have a lot of like self-made filaments where you get the simulation run. Just a lot of feedback and cooling back down.
I wouldn't say there's self-made filaments. You definitely have a different structure, and it's more spread out and it's more kind of clumpy because it has I would say the strongest probably feedback of all of these, and so it also has the lowest star formation rate of all the galaxies because it's constantly blowing the gas very strongly back out into the IGM. But in terms of filaments, I'm talking about the actual like large-scale cosmic web itself. I don't know if that answered your question or not. Okay, so you may ask the question, whether you believe me or not, do these cold flows really exist? Here's just another snapshot again of our ENSO simulation at redshift 3. Again, this is the size of the virial radius. Here's the density contour of the disk. And here's the kind of red-blue rotation of this massive disk. So despite the fact that these have very different hot halos, very different star formation rates, they're different codes, different feedback schemes, one thing that we found basically in all of these was that the existence of these cold flow disks seemed to be an actual thing, not just a weird like code variant thing. So you have these cold gaseous disks. They can extend upwards to half the virial radius, maybe not quite that high in all the simulations, but some of them get that big. They're kinematically linked to these inflowing filaments, as we saw the large scale. That's what's feeding them. And so they're thought to be very short-lived, right? The gas should be flowing down onto the galaxy. So you might argue that it should probably, we haven't looked at metallicity yet, but it should probably be low metallicity as well because it's this fresh and flowing gas. This seems to be a relatively robust prediction of lambda CDM. At least all 4 of these simulations show that these cold flow disks actually happen. Despite that, you may ask me anyway, but do you, like, for real? Like, do you really expect to see these in kind of the real universe, not just your simulations? Luckily, as I was preparing this talk, 2 weeks ago, a recent Nature paper was released by Martin et al., where they observed a giant protogalactic gaseous disk with smooth rotation kinematics. So here's the disk, its rotation curve up to, I think, 300 or 400 kilometers per second. And this disk was linked to the illuminated filament reported by Ken Lupo et al. 2014. So here's the filament. You can see the filament up here. You can see the filament is kinematically linked to that side of the disk. It's flowing in with the same kind of blue shifted signature there. The disk is huge, 125 kiloparsecs. By looking at kind of the dynamics of this, they were able to estimate the dynamical virial mass of this system, and they were able to get the virial radius estimate. And so this is about half the virial radius of this particular galaxy. They were able to compute the angular momentum of this material based on its rotation and figure out the spin parameter of 0.14, significantly higher than spin parameters of dark matter halos or stellar components. And now the system that they are observing here is about a factor of 10 more massive than what we were simulating. So their disk is more massive, bigger rotation velocities, but when scaled to the virial radius of what they're looking at, very similar to what our simulations were just showing. So do we expect them to really exist? Should we expect to find a cold flow disk in the real universe? I would argue that it's already been done. We just found one. Well, no, I wasn't involved, but someone just found one. Okay, the summary is this new picture of angular momentum. Is that robust? We looked at these simulations, different codes, different feedback. Since I'm running out of time, we found gas is higher in momentum than the dark matter. The filamentary gas, cold mode gas, is higher in momentum than the hot. And since there's a non-zero impact parameter, naturally, these kind of fire hose streams end up rotating around the galaxy and creating these cold flow disks that extend to half the virial radius. So is this qualitative picture robust? I would argue yes. But of course, the details, as you saw, the exact structure, what's the exact size, how much mass is in these disks, that's going to depend on exactly which simulation you're running, what feedback scheme you have, and all those nitty-gritty little details. But there is evidence of observational confirmation of one of these things, so I think they actually exist. Thank you.
Thank you.
Concerning the observability of this outer extended disk, first I want to comment that a few other papers indicated detections of something consistent, like by Nicolas Boucher and others from last year or a couple of years ago. But we are far from really seeing many of them. In terms of the likelihood of observing them, what we found in our Dunwich other papers is that if you pin through random lines of sight, about 30% of the times, the column density of the Lyman alpha or neutral hydrogen in absorption is 30% of the time like damped Lyman alpha systems. So yes, it's pretty likely that 30% that you will see this with high column density in Lyman alpha.
So can you go back to one of your comparison plots where you had the three or four codes depending on the epoch? Okay, so I was just wondering if I can ask a provocative question. I note that the Gizmo simulations seem to have lots more sort of cold clumps. This is sort of what the old SPH used to show, and I thought it had been banished in the new SPH. It seems to be back. Would you care to comment on what's going on?
That is a provocative question.
Is there anyone in the audience who'd like to?
They won't do English codes yet.
All right, so we do see more clumps in Gizmo PSPH when we put the strong feedback on. If the feedback is off, there are essentially almost no clumps. So I think at this point there is the likely possibility that this is some numerical artifact to some extent. Whether it affects actually the evolution of some of the galaxy properties or so on is not clear.
Yeah, also I just wanted to add for the number of these cold disk flows. I was in Hawaii last week and Chris Martin presented this result, and he said they've looked at other objects. I think it's 3 or 4, and in all of them they see these cold flow disks. So wow. Stay tuned for this.
don't think I can take everyone. I want to take Nicholas this time.
It's just a comment that also in absorption, if you select from, say, a stronger ionization like magnesium, you find that their distribution is not symmetric around galaxies. You have a strong peak in the distribution around major axis, and another strong peak around the minor axis. So the minor axis could be outflows, and the major axis is very consistent with this picture of cold flow disks.
Awesome.
The last one. I think the rest we will have to do with the
So among the many things that seem to be similar in these different simulations is the existence of cold flows. And the reason that I mention this is that one of, not in this series, but in some of your other series, you include the AREPO simulation at higher resolution than any AREPO simulation I've seen before. And it looks very much like the other high-resolution simulations.
Yeah.
But in some of the very recent illustrious papers, they're still saying that they do not see cold flows, and they strongly doubt that they really exist. So can I now take this as evidence that if you run a repo at sufficiently high resolution, i.e. you are doing about 90 parsecs, then you will, just like all the other codes, see cold flows?
Well, I think, hopefully I'm remembering correctly, but it's not that the cold inflowing gas doesn't exist, but I think one of those papers is arguing that it doesn't make it all the way to the galaxy without shock heating. And so far, I would say that our simulations are definitely showing that you make the cold flow disks. Now, if you want to argue that that gas doesn't make it all the way down into the galaxy before it shock heats or something to that effect, then maybe you can define cold flows as not happening. But we definitely see the cold flow disks, just like the other simulations.
I'm sorry, the rest we leave to the half an hour discussion at the end. It's not long.